I promised you some pictures to clarify where we were at. And as usual, I claim it's all important what we do. And it's going to be important today also. Where have we been? Let me just summarize this in a sentence here. Starting from the general realization that sines and cosines are important, and knowing that sine and cosines are special cases of exponential functions, we have built representations for signals that don't need to be strictly periodic anymore on some interval like we had before, but that rather span the entire real line, and whose only requirement is that they are square integrable, which means don't have infinite area. And we said, all right, that gives us a continuous time, continuous frequency representation, as in C here, which is probably the most important one if you're doing physics, because physics or mathematics usually ignores the subtleties of sampling and band limitation that I'm starting to discuss until later points where they become important. So your typical math course is going to talk about the continuous Fourier transform because, here it is. That's C. Okay. And you want to look at that and go, all right, the signal S of t is the transform of its Fourier transform, S wiggle, of frequency. So time goes to frequency and frequency goes to time. And if everything is properly normalized, the only thing you need to do to go from one place to the next is to change the sign of your exponential, also known as complex conjugation, and you integrate. So very simple symmetric transform, unitary transform, doesn't change the length of the signal, doesn't change the norm of the signal. All those things are strict and important things. And they map a continuous time axis to a continuous frequency axis from negative infinity to plus infinity. Okay, so people will talk to you and say, this is the Fourier transform. Then I'm saying, well, or is it? Because you're going to be a scientist, you're going to be sampling a signal. And so your S of t, which you claim will exist, is really only existing for you on your measurement strategy. Your t, which is now an index, delta t, which is now a sampling step. So the time axis is discretized. Should we use that word? Or rather, should write that word. Discretization. And Dirac's name came up, and some people like to write this operation as a Dirac comb convolution, which is just a fancy way of saying take a sample already, then wait, take another one, then wait, take another one. And right here, we're dealing with equal sampling. There is a side story there where that's not necessary to do knowledge and to gain knowledge and inference. But for here, for now, it's convenient. And so there's a single delta t. If that's the case, we need to build a transform for that, and we'll just start writing it, but we know that something happened, so we make space for something being changed. And we notice these limits, and then we'll write this Canada transform, and we're noticing immediately that sampling in the time domain periodizes in the frequency domain, because whatever we get repeats in the frequency domain, which didn't used to. And then we said, well, what is it that we have gained or introduced, gotten? Well, we try to write the equivalency, or rather figure out the relation between this new thing which we have introduced, S wiggle of p, so the periodic, apparently, Fourier transform of a sample signal. It's periodic in the frequency domain, apparently. What does it mean? Well, it turns out that this periodic frequency domain Fourier transform of the time domain signal S ends up being composed of the true pieces of the Fourier transform at the proper frequencies, but mixed in there pieces from outside this frequency band 1 over delta t where they weren't. In other words, they were assembled from those pieces plus those pieces outside where they clearly were, but you wrap them inside the frequencies where you now get them and you can't undo that. All right, that was a poor sentence, but a picture will clarify this, okay? Continuing on, compare and so on, we are dealing with the discrete time continuous frequency transform. Well, let me just draw that picture. So we used to have a continuous time axis, and we used to have a continuous frequency axis, and they would stretch forever and ever. And blue would be some sort of a signal. It doesn't have to be a real value, but make your life easier and think about it as something real, like the temperature. And it'd be like this, whatever. That's been our SFT. And all we're saying is that this signal, when integrated between those limits in the mean squared sense, so its norm, by this definition, is finite. Okay, that sets up the proper space of functions called the Hilbert space, if I didn't mention this already. And I don't claim any truth to my rendition here, but let me write the amplitude of the wiggled transform just because, and this is important, even though my signal is real, S of t is real, my Fourier transform involves correlation of that signal with e to the I something, which means the result is complex valued, which means it has a real part and an imaginary part, and all sorts of connotations that I won't get into now. But if I just look at the length of that vector and I square root it, so I'll just do the absolute value, then I'll get something strictly positive. Positive, it could be 0. So without any claim to matching the signal in any way, I'll say, well, here is its Fourier transform in absolute value. This thing that I'm drawing here is the signal, the usual, and I dislike using the term, but I'm going to do it anyway. What I'm drawing here is sometimes called the amplitude spectrum. I'll tell you I dislike using it because of the many more things I'll need to tell you about the spectral density, which is different from this, but related, and people confuse it at their peril. Right now, the thing on the left is easiest to understand. Absolute value of whatever you get after doing the Fourier transform of the signal per transform pair C in my notes from before. Okay, so we're claiming these things exist. Then we're going in as a scientist or an engineer, and we're sampling this on a grid. And the samples are delta t apart. And so you don't know the full extent of the signal. You only know it at these points. It stands to reason that you know probably less about the signal than if you knew everything. But that's precisely what we're trying to quantify. What our formula tells us is probably best illustrated as follows. I'll go with, sampling in the time domain. That's my symbol here. Leads to something that I'll be drawing. Okay. How about I draw a 0 axis on my frequency axis? And I'll say this signal, I'll draw some more markings. So I'll draw 1 over half delta t and plus 1 over half delta t. And reading my own formula from before, it tells me that now I'll just hatch it, I guess. I'll just say leads to the newly periodized amplitude spectrum. So it says the following, right? I'm just reading now the previous page. And I'll read the periodized spectrum was begin with some normal frequency is the true spectrum of that frequency to begin with. And then you know it repeats with a period of 1 over delta t. But also, you know that you're not done because at the target frequency, you're also receiving a contribution from outside of the interval once, twice, 3 times, and so on. So I'm going to try to draw that here and say that within the band of interest, sorry, not of interest, within this band, and this is my definition of a band, is a frequency range, and which band it is the one between negative delta t, 1 over delta t and plus delta t. So it's getting what it needs to get, namely this, but then it also gets, for every frequency that you had here, this is some f here, you're getting the power that was at f plus 1 over delta t, and you're getting the power of f plus 2 delta t, which I'll just say, you know, it's wherever that was and wherever this is. How about I mark it a little dot here? And that now comes in and piles up on top of that frequency that you're targeting. I realize I need to make space, so I'll just box this as a label. So there is this frequency that you want to know something about, and it's the right thing plus the thing from outside, plus the thing that is coming from twice outside, plus 3 times, plus 4 times, plus 4 until whenever. And so that adds itself onto this new transform, which was S wiggle of P at F. So these samples here give me S of T dt. I had S wiggle of F, and now I'm drawing S wiggle P of F, and it is now it's going to be hard for me to draw this properly, so I'll just you know, sketch it here. I should do it properly, but it gets new contributions that weren't there before. I'll just sketch it here, which, oh, here's a good way of doing it, which are, you know, extra bits coming from outside, and here is the extra bits. So all that is untruth, right? If you're getting the Fourier transform of a sampled signal that really look like the red line, and you really should want to know about the red line, and you're trying to get to know it, but you're doing this transform, you're not getting what it is. You're getting the red line plus the contributions from outside of the interval that you can get, which is set by the sampling rate. And then not only that, then it periodically repeats. So I'm no longer to scale here in any sense of the word, but so then that thing repeats, because remember, it was periodic and its extensions. Okay, so shown here in between the interval, -2 and 1 delta t, and then periodically repeating as marked here by the dashed line. Okay, that's how to read this formula. And the phenomenon by which you get these extraneous contributions, right? Remember, this is what you really want, whereas the blue stuff is which is what you get. So the process by which you get these extra contributions is called aliasing. Okay, these things refer to frequencies that contribute power to what you think about what the power is at some other frequency. And here I was trying to, yeah, right, I'm quoting from Karl Marx, those who do not understand it are condemned to foolish results, which I thought was a funny quote. Pity the fool who doesn't know aliasing. Okay, consequences give me two ways by which I can suffer less from aliasing. One,
you can sample more often.
Yes, sample more densely. What's another way by which you don't have this effect? Maybe not something that you need to do. Be more band limited. Don't have that much to fold into it, which means, I'll just say it, be more band limited. And now I'll just draw that here. If the original true signal had a fast decay outside of this band, there'd be less to rope in, there'd be less to fold in. So here's the band of what you can get. Here's a miniature zoom of my figure. A signal that's fast decaying outside of this interval gives rise to less aliasing because, you know, there's less to grab from outside. Okay, now that is victim blaming because it's not the signal's fault that you're not sampling enough, but it's a useful construct. Okay, consequences for, you know, remediation, that'll be one. Number two here is, you know, don't have the problem. It's less prominent. Other consequences I want to talk about is, what if the underlying signal SFT is truly band limited? That's going to get its new sheet. Oh, and I'll make more picture, one more picture. Consequences, you know, it's wrong. I think this is a good picture to take here, to make here. The true signal is some sort of a sinusoid, as I'm going to draw to the best of my ability. And I'm going to draw the result before I draw the thing that gives rise to the result, just because it's easier for me to draw. Actually, I should make it in black. There is a way, am I drawing this right? I'm going to try, that I can sample that blue signal evenly. If this were my delta t, or my true signal, then the effect of aliasing would make it seem like I have this different sinusoidal signal. What I think SFT really is, if all I know is the samples at these blue dots of SFT, same notation as before, and I try to reconstruct it, which I haven't talked about, but I want to give you the visual anyway, as you think that this is, you know, a low frequency sinusoid, when really the underlying process is more fastly varying. This is the effect that you see in movies, sometimes still, where or actually I've seen it on the highway with my own eyes, where it looks like car wheels are rotating backwards, even though you know that the car is going forwards because you're in the car next to it. But the way the hubcaps and your frequency of your eyes interact, it looks like it's going the wrong way. Now here I'm showing it, I'm not showing any direction or anything, but I'm just saying a true blue signal, when sampled at the blue points, if you're trying to make something out of it, which I haven't taught you yet, you'd make it into a black signal, which is completely different from the one you have. And the bottom line is you have to assign power to a frequency that it doesn't even have. That is the telltale aliasing. So in keeping with the previous picture where this was a frequency axis, right? This would be the 1 delta t, plus and 1, negative. How do I turn that into a negative? Without messing it up.
Frederick, what does it say to the left of like 1, 2, and 4?
This one says remediation. This is my keyword for, you know, how to like not have it, remediation. How to be less prominent in this detrimental effect. That's, you know, just be better, be like Ted. 4 says it's just wrong. It's like, what do you make of it? I'm trying to give you some heuristics, which is a excellent word to use in polite company. So negative 2t plus 2t 1 over. That's just a little scheme, right? So here's my same drawing. And so what does it mean? This blue signal that I had, its true Fourier transform. Let me just give it an actual sinusoid at some frequency. So the original red curve would have been empty inside that band, which I've been mentally shading. And when you sample at delta t, you're just getting this in the wrong place, and it looks like you have power. It's a ghost. You get that stuff here, where it doesn't belong. And that's my visual for aliasing. An originally empty bucket gets filled with things that leak in. Leakage, by the way, is a word for it. These frequencies, their power aliases into the power that you're querying. You're asking the power at F inside the bucket, and you're getting actually confused by the power outside of it. And so that's how you can turn one sinusoid into another one at a lower frequency by aliasing. And that's why you're condemned to foolish results if you don't know this stuff, because you wouldn't know. You would never know. So another point is that you shouldn't even ask. But I'll clarify that. There's actually a corollary to this here, which I'll clarify. Okay, so let me just go to the truly band-limited signal, where we can make another result that makes a lot of sense. So I'll call it band-limited signals and the sampling theorem. I'm going to now relax, or rather specify. I'll say a band-limited signal, and I'll call it S. And maybe I'll just be super precise and say, I'll call it S of W. And it's going to be a time function. And I'm going to define it from its continuous representation. So I look up, I shouldn't have to look up, right? You should remember these things by now. I'm looking up the Fourier representation of this signal, as in the Fourier transform, e to the I2 pi ft, integrate over all frequencies between negative infinity and plus infinity. And here I'm saying that this signal actually is all of that. I was doing some black earlier. Oh, my frequencies were red earlier. All right. E to the I2 pi red frequency t dt. And now I'm just saying, look, this signal does live completely on the interval. So that's that extreme case where I was working towards the frequency axis, while in principle going from negative infinity plus infinity, literally contains all the information on this particular signal with no contributions at all from outside a certain bandwidth, which I call W, or really 2W if you want to be precise. And by the way, half the books use 2 and the other half don't. So you'll be, if you're wrong, check if you're not wrong by a factor of 2. All right. So think of an amplitude spectrum that literally does not have any power outside of the band of interest. Okay. Well, should I say it even more precisely, right? This does mean that S of these frequencies, S wiggle, is 0 when the distance on the frequency axis is larger than W. Okay. So we know that in that case, that periodized Fourier transform at frequencies F is right. It is the Fourier transform of the signal at those same frequencies. Okay, periodized, it returns, but inside the bandwidth is unaliased. It is not aliased. Okay, I'll write the same thing. I'm going to do a smaller then, right? So a signal that didn't have anything to alias outside of W can be known exactly within W. And sure, the S sub P periodizes, but that's all right, small matter. Okay, so now the connection between, sample more densely, sample the signal, with a delta t. And when W is 1/2 delta t, then you have this fortunate situation. So why am I doing this? I'm saying, look, I'm turning it around. If I have sampled at delta t, then I know that I'm getting contributions out of the band delta t. Now I'm saying, well, what if there were no contributions? That's the same as saying, if I have a certain target that specifies how I need to sample in order not to get these contributions. And why is that important? That's important because then, were I to reconstruct what I think my signal was, were I trying to attempt to reconstruct S of t from its sampled version, I would get the following, which I'm going to get to, right? So here is the continuous time signal that I'd like to know something about. That's truth, which comes back in every lecture. Like the thing that you know is there, but you don't have it. You just have samples of it. From the discrete time sampled version, and please don't forget for a moment, right, that this t, the second t is an index, the delta t is an interval, and this t that I mean here is a continuous variable. It's slightly confusing, but well, so be it. All right, were I to reconstruct, try to reconstruct, I would write down, I would go look up my definition. I would go, okay, let's take a look. And I would say that S of t, in that case, would be the inverse transform 1/dt, 1/2 delta t of S wiggle of f e to the I true f. I'm just writing again. Oops, and the one on the top, there is one mistake on my board, and that is that this should be a frequency, right? The frequency integrates out. Up here, that became a red f, right? F dummy variable, you get a t back. F df. Right, I'm merely restating. So I'm trying to make the connection between a continuous signal that is band limited, which I have now sampled with a delta t, and the delta t here is matched to the bandwidth of the signal. And I'm trying to learn the true nature of this signal SWT that I can get revealed to me after doing this operation. So I'm saying, what is the relation of S of t to the sample signal? And so now, this is not going to be pretty here. How about I start a new page? And I'll just say, what would I get? No need to erase. I'm writing again S of t. I know it's fully contained. Simply copy. I have a transform. I have it at frequencies within this bandwidth. I write the full transform, and I make sure I integrate over the frequency. All right. That's what I would get. Rather, I don't know yet, but I know I need to start there. So now I need to use something I've already used before, right? Now I'm going to go look up in my earlier notes what the definition was of this transform, or the periodized transform, doesn't matter, because they're identical in the interval. It's this infinite sum, right? So I look up D from back transform pair D, and I substitute, and maybe I'll just write it so we don't have to do the whole thing. I insert that from there, and I'm reading it off my sheet here. I'm going to give it a t prime because I need to keep this sum contained, right? So t prime from negative infinity to plus infinity. And what does it contain? Well, I'm literally copying from my sheet on the left here, which is that D transform on page 63. And this is dt prime where I'm at, delta t. And it's an inverse transform, e to the negative I2 pi of that f I'm looking at. I get a t prime because I'm expanding the interior of it, and I already had a t, so I need to not get confused. Delta t times another delta t. Okay, so that is just reading off, and whether the p was here or not, it doesn't matter because I just made the argument that within the band, there's no difference. So that's coming from transform D on page 63. And then the best way, maybe I'll write the next step fully, is to switch to sum and the integral to pull out the term in t prime and to ingest the integral into something that is doable on its own. And I have 2 pi and I have an f, but I got to combine the exponentials. And so I have t, the original one, minus t prime delta t df. Okay, maybe this is the most math we've done in a while, but it's not complicated. It's just summing and multiplying exponentials. I want to do one or two of these things here because in this literature, this is literally all they do. They take it together, they use orthogonality, integrate, they switch to sums, they square things, and it is a bunch of writing and bookkeeping, and there's really no way to get confused if you make sure that whenever you're expanding a sum into an integral or integral into a sum or whatever, you have things inside that you add primes to it so that you don't have your variables confused. Your dummies need to integrate out. And then there's typically something like this. You either do the trick from last week where I said, you know, instead of integrating over the whole integral, chop it to pieces and sum it up. And here this is it's one of those things. So then there is this fact that, and I'm going to leave that for a separate page here. This here, you then go, all right, I got to go integrate that. Oh my God, right? E to the I2 pi something over some limit. Integrate this. Please do it in your spare time. And then realize, I'm just going to help, I write it, right? I write the result. It turns out that is the sine of pi of t minus t prime dt, delta t, over delta t, and then the whole thing divided by pi t minus t prime, delta t. And these things come back so often that they get their own name, okay? So this function is named the cardinal sine, or the sinc function of t minus t prime dt over dt. And again, in the literature, you're going to find different definitions of what the sinc really is, whether there's a pi in there or not. Right here, right now, this is the one. And I'm writing all of that because I want the result, right? So I want to know, what do I make of my continuous signal to which I don't have access from my samples to which I have access? And now you're going to say, but you don't have an infinite amount of samples. And I'm saying, no, you are right, but we're going to get there later. Now I'm just saying, what does sampling do if you could do it forever? Well, here's what that does. It says that you're messing it up, you're periodizing, but if you have sampled it appropriately, it's not aliased. And if you wanted to reconstruct the signal from its samples, you would get it right back, because the relation between the sampled version and the original continuous version is through this formula, where it says take your sums and take the sinc function of t minus t prime dt in the following manner. I'm going to box it because it's a very important thing. How to reconstruct a signal from its samples, okay? And you can hopefully tell that all the inference follows from that, right? when we were dealing with distribution, it was like, oh, I have a Gaussian distribution, but I don't know which one. So I'll take 37 samples. I need to be able to reconstruct it. When we did inversion, we said, some model set parameters through some models produces data, and we really want to know what the model is such that we can, well, reconstruct the data or interpolate the data or extend and extrapolate the data. In other words, do inference or imputation or whatever other names come up. So here, that's the same thing. One last time, I'm going to say that this is what we know about the continuous time signal from its discrete time sample thing. And I realize now that I've given you this special example of a band limited signal, which I've given a subscript SW. So I'm going to give you the subscript back for full disclosure. I'll just put a SW underneath everything where appropriate.
Frederick, should there be a delta T next to the discrete time in the boxed equation?
You know what? I think this needs to close down into the definition of the sink, which absorbs that delta T. I should verify that. But yeah, no, that is the case. This is the one you're missing, right? And I'm just sucking it in here. I only made a mistake in boxing. Again, you do want to verify this. I did verify this, and I also want to stick with some notation convention which is not shared by everyone. You'll look up sign sync and you'll find two versions. But unless I, finish the lecture and go like, oh my God, this was totally wrong. I'm not actually thinking about this. I know it's coming from there. I'm not verifying it. I'm just saying that's what it is. So go triple check that. But there it is. I'm going to just add the W's everywhere, right? This thing is all applied to a special class of signal. Just that you realize that today we're reconstructing a band limited signal from its samples when those samples have been taken at 1/2 delta T in relation to the bandwidth. That's a lot of W's, but there they are. Okay, continuous time, but band limited. So maybe this does give me the opportunity to verify because I'm looking at my notes here. Sinc of x, my definition should be the sine of pi x divided by pi x. And that's why the delta T needs to go there, because I need it in the denominator. So it's pi over delta 2 in the denominator, and that's where I grab it from. So I claim what's on the board is fully consistent. All right, so a couple of things to note. First of all, this has a name. It's called Whittaker-Shannon interpolation. Whittaker-Shannon theorem. The whole thing is a theorem. The procedure is constructive. It's an interpolation procedure. It's to say, well, what if you have interpolation, right? It's the procedure by which you go from, and now I'm going to draw that ridiculous example again. If you have samples, and maybe I shouldn't make a beautiful sinusoid because you're first going to have multiple components, and I want to turn that into the continuous signal that it may have come from. Well, my inference is that I do this procedure. Whatever I get out, I'm going to get it out like this. It provides my way to reconstruct the signal from its samples. And I'm making a bit of an exotic mess out of here, but there you are. All right. That's what I would make. That's what I would claim is my S of t from my ST of delta t. And the conjunction with the previous thing here is that clearly, if you did that with that already alias signal, that black line here would be what Whittaker-Shannon would interpolate, and it would be wrong because, yep, it's not band limited, right? So that's how the two pieces connect here. But this theorem does tell you that if you're sampling at the right rate, that you can know everything there is about the signal within its band, and you don't need to overdo it. Then there's some additional words here. This sampling at the Nyquist rate, okay, and the Nyquist frequency as 1 over 2 delta t. This is really the definition here. So the Nyquist frequency is 1 over 2 delta t. So if a signal is band limited to W and you sample it at a rate 1 over delta t, then you can resolve the signal, completely know about it, not have any aliasing, completely reconstruct it within the band plus and minus 1 over half delta t, which has the width 1 over delta t. Okay. Consequences, heuristics, implication. The don't even ask comment is sort of saying, look, here's another way of thinking about it, that if you want to recover a true signal that has a certain frequency, then you need to sample it at least twice per wavelength. It doesn't mean you have to sample at the tops of these things, but I'll just draw it like slightly offset here. You got to get one here. And let me say I sample at twice the wavelength. Then I have a chance of reconstructing the signal. I want you to see that if you sample at slightly less twice the wavelength, then with every passing sample, it's like I'm moving down this thing and then down again and down again. And that's how I'm going to get a fake oscillation if I try to reconstruct it, because I'm not sampling at the right rate. So the safe thing is to better than this. And so if I sample at, double that, then you and I will know visually that this sampling rate is a really safe rate. This is a delta t that is smaller than, there's one frequency here. So let's call it that one frequency. That's the wavelength. And you have this at this. Okay, it's getting to be very small, right? Maybe I should say these crosses are sort of the additionals. I don't like my legend. So this sampling process, which I'll just say, the dot cross sampling, right? I mean, look, that's smaller than twice per wavelength. If I just did dots, then I would say, well, this is twice per wavelength. If I did it very poorly, if I sampled my signal at a much too low rate, like this here, then I would get serious aliasing. That's the nature of the don't even ask comment, is don't think that you're going to get frequencies right if you haven't sampled them right. It stands to reason from our regular interpolation ways, from a regular inversion, which I did 1 or 2 times ago, where you say, if you think of this as a linear problem and you try to reconstruct one sinusoid from its samples, that you are just going to get it wrong if you're not you're missing beats, you're missing oscillations. This gives the formal version for how much you really need to sample. You need to sample at the Nyquist rate, and that is because of this formula that says if a signal is band limited to negative W to plus W, so it has a bandwidth of 2W, then you can completely reconstruct it from its samples, as long as those samples are taken with a spacing delta t, which is the Nyquist rate, or the rate would be 1 over delta t, and then you can reconstruct it using this interpolation. So I want you to take one final look at this theorem and tell me one more thing about it that you find potentially of interest. What sort of an equation is it? I'm asking a very general question. Anyone has any ideas that tells me some words I can apply to describe this equation?
Convolution of some sort. Is it a convolution of some sort? Yeah.
Yes. So explain why you see that.
I mean, you have this shifting axis of t prime. I mean, I see it as an f and an h, just a mathematical form. And you have these sinc functions. And you swipe the sinc function across the sample data point to get the
Well,
continuous.
so the convolution reveals itself by being what comes out is a T. There is a kernel that varies in T, and the T primes are dummies over which is being summed. Okay. So please, everyone, I want you to immediately recognize these things. I'm going to go back to my own notes. So immediately I want you to think about constant diagonal matrices. Somebody else give me the name of a constant diagonal matrix that we surely discussed, but I'm now looking up myself to make sure we did. Ah, okay, well, we'll keep talking as we do. Convolution, remember that was here. Look at it, right? Same form, N, N, K, K, K. Remember this? Toplets, you have to immediately recognize that there is a constant diagonal matrix. Whether that's a sink is irrelevant. The sink is the specific form of this interpolation kernel. This could be anything. This is a convolution equation. It's a discrete convolution equation. Why I am bringing this up at the very last minute is because, how many more lectures do we have? Very few, 2. I then need to make it immediately intuitive that what your reconstruction formula is a convolution with a sink. Well, let me just say, in other words, we need to understand and will the relation between convolution and the Fourier transformation. And I'm going to say it here so it's on the record. We'll be seeing how band limitation is the act of taking a Fourier spectrum and just multiplying it by a passing window that's rectangular that says, here, these frequencies I have, these ones I don't. If you do that, as we will see, that's the same as convolving it with the Fourier transform of that rectangular window, which is the sink function, which I already know because I'm already kind of defining it here. You should want to see that that is the Fourier transform of the function 1 in the argument t minus t prime, and 1 only over the interval. So it's all connected, right? And it's going to come out, and you will have an explicit relation between convolution and Fourier transformation, which will serve you very well. And you'll understand sampling and band limitation. And then you make sure that you don't overdo things by oversampling, and you won't underdo things by undersampling. And when you do neither, you'll have unaliased knowledge. And when you can't, you will just understand the aliasing that you get, and you will fold it into your interpretive framework, knowing that, you just can't undo it, but you can understand it and you can deal with it.